So we're talking about section 3.5 today, related rates. And the idea here is that, when you have a formula, so for example, the area of a circle is pi r squared. But suppose that your circle is getting bigger and bigger over time, right? So that would mean that the radius is increasing in time, and that would also mean that the area is a function of time. And so you could write then that the area as a function of time is pi times the radius as a function of time squared. Okay? And so when we differentiate this with respect to time, right, we would have dA over dt is equal to pi, and now because this is a function of time, right, that would be 2 times the r of t to the 1 power times r prime of t. And this is by using the chain rule, right, or dr over dt. Okay, so that's different than if you were to take this and take dA divided by dr, right? So that's differentiating with respect to r. And so in that case, that would just be pi times 2r. Oops, pi times 2. I'm talking and writing at the same time. 2r. It would just be pi times 2r. And so that's the difference, right, between differentiating with respect to the variable here, r, versus assuming that r is actually a function of t, right? Because if r is a function of t, then this is actually a chain rule, and you have to multiply by r prime. Good. So we might ask something like, if the radius is expanding at a rate of let's say just 2 feet per second. That's a big number, but that's okay. What is the area, or how fast is the area increasing? I'm just making this up as I go here. How fast is the area increasing when r is equal to 2? Oh, I'm using the same number. How about r equals 3? Good. Then, we would start off with our circle, right? And so the basic formula here is that a is equal to pi r squared, just like before. But now remember that we're treating these as functions of time. And so when I differentiate, this is how fast the area is increasing or decreasing, dA over dt. And so if I differentiate this side, that would just be pi times derivative of r squared would be 2 times r of t, right? That's to the 1 power. And then you have to multiply by the derivative of the inside function dr over dt. Okay, and so now we're given that r is equal to 3 and dr over dt is 2. Good. So how fast is the area increasing? It would be 2 times 3, that'd be 6, times 2 is 12, so 12 pi dA over dt is equal to 12 pi. Oop, not 12 over pi, 12 pi. Good. All right, so this is what we mean by related rates. In this case, the area was related to the radius, right? And they're both changing in time. Okay, let's try another one, maybe a little bit harder. So let me check to see what number this is. This is activity 3.5.2. Okay, and so we have an inverted cone, and we're told that it has a radius of 6 units, whatever units it's using, and a height of 8. And so the idea here is that water is leaking out of the bottom. Okay. Oh, I'm sorry, water is being pumped in. Okay, and so let's go ahead and draw a couple of things in here. We'll take r to be the radius of the water, and h to be the height of the water at time t. Good. And so now we're going to be told that the volume at time, well, the volume of a cone is 1/3 pi r squared h. Okay. And so in this case, we're treating everything here as a function of time. So volume of time is equal to 1/3 pi times the radius of time squared times h of time, right? Okay. Now, we could differentiate this directly. dv over dt, this would have to be a product rule, right? But let's see if we can get this in terms of one of these variables instead of two. That just might make our life a little bit easier. Although, like I said, we could differentiate this as it stands. But let's see what else is given here in our problem. Let's see. Determine an equation that relates the volume of the water at the tank at time t to the depth at time t. So we would like to try to find a formula for volume just in terms of h alone. Can we find, or can we get the volume in terms of h alone? Well, you might notice that we have something special going on with our triangles here. So if I redraw these, right, this would be our 6, it's laying sideways, right? And then this would be r, and then this would be 8, and this would be h. And so we can use our similar triangles, right? So you could write that relationship lots of different ways. One way might be 6 is to r as 8 is to h. Oops, 8 is to h. Good. Let's see. I'd like to get a relationship between r and h, so let's go ahead and cross multiply here. And so that would be 6h equals, am I still on the page? Oh, let me check real quick. Yes, I'm still on the page. Good. 6h is equal to 8r. And now I'd like to substitute r, something in for r. So let me divide both sides of this by 8, and I will get 6h divided by 8 is equal to r. Okay. Good. And now h then is going to be 3/4, or sorry, r, let me write this down here. R is going to be 3/4 times h. Good. And this relationship holds through time as well. So r of t would be 3/4 h of t. Okay, so now I've got something I can substitute in. So now I can write volume as a function of h alone. So that's going to be 1/3 pi and then 3/4 h squared times h. Let's simplify that a little bit. 1/3 pi, that's 3 squared over 4 squared. H squared times h is h cubed. Okay, so it looks like this 3 cancels with one of those. And so we get that volume is pi over 16 times h cubed. Okay. Oh, I missed a 3. That 3 is still there. Okay, good. Now, remember that h is actually a function of time. So this is actually volume of time is 3 pi over 16 times h of t cubed. Okay. Good. Now let's see what the question asks. Let's see. Find the instantaneous rate at which the water level is rising when the water in the tank is 3 feet deep. So we want to find the instantaneous rate at which the water level is rising. Instantaneous rate at which the water level is rising is dH over dt when the water in the tank is 3 feet deep. Okay, so I don't know what time that is, but that's fine. I don't think I'll need that. Uh, let's see, do I know anything about the volume in the water in the tank? The water is being pumped in at a rate of 4 cubic feet per minute. Okay, so that means that dV over dt is a constant, and that is a constant 4. Good. So I think I've got all the pieces that I need here. Let's see if I can differentiate this and figure out what dH over dt is. So dV over dt is equal to, the 3 comes down, so that'll be 9 pi over 16 times h of t squared, and then we multiply by the derivative of the inside function, which is dH over dt. Or you could say h prime if you want. Good. Now I know that dV over dt is 4, so I'll go ahead and put 4. And then I've got 9 pi, am I still on the page? 9 pi over 16. Then h is going to be 3. Good. And then we just are left with dH over dt. Good. And now we just solve this equation for dH over dt. And it looks like dH over dt is wait a sec. Okay, so I see 9 times 9 is going to be 81. So that's going to be 81 pi over 16. And so, let's go ahead and write one more line. 4 is equal to 81 pi over 16 times dH over dt. So, therefore, invert and multiply, right? So we're going to have 4 times 16 is 64, I believe, divided by 81 pi is equal to dH over dt. Good. And so that is approximately, if you plug that into your calculator, 0.25 feet per minute. Good. There it is. Now the activity goes on for other different values of h, but we'll just stop there for h equals 3. The main point here is that what are the related rates? You know, when you write down the initial equation here, you can think of volume as changing with respect to the radius and the height, but the radius and height are functions of time, so that makes v a function of time. And so when you differentiate, right, you have to be sure that you're differentiating with respect to time and not with respect to one of the other variables. Good. I'll stop there. That was kind of a long example, but I wanted to go through that one carefully. We'll try another one. We'll go through that one carefully too. See you then.